Professor Belfrost's science class is back.
Oh yeah, hi. Welcome back to another lesson on chemistry with me, Professor Belfrost. And today we'll cover. Actually, we'll just continue the last lesson. Still on the chapter on matter, physical and chemical properties, elements and compounds. And we have I've done explaining to you about periodic table, right? And today we'll move to um the molecular bonds and the ionic bonds, okay, but the naming nomenclature will be on the next video, I think, with the revision, I think, or maybe two videos, I don't know, let's see. Okay, so here's a review, a quick recap on our last lesson. So first, a chemical symbol is an abbreviation that we use to indicate on an element or an atom of an element. Some symbols are derived from the common name of the element, others are abbreviation of the name in another language. Most symbols have one or two letters, but three-letter symbols have been used to describe some elements that have atomic numbers greater than 112. To avoid confusion with other notations, then only the first letter of a symbol is capitalized. The symbol for a specific isotope of any element is written by placing the mass number as a subscript to the left of the element symbol. And because its proton and its neutron contribute approximately 1 AMU to the mass of an atom, and its electron contributes far less, then the atomic mass of a single atom is approximately equal to its mass number. However, the average masses of atoms of most elements are not whole numbers because most elements exist naturally as mixtures of two or more isotopes. A molecule formula is a representation of a molecule that uses chemical symbols to indicate the types of atom followed by the subscript to show the number of atoms at each time in the molecule. The structure formula, on the other hand, for a compound gives same information as its molecular formula, but also shows how the atoms are connected in the molecule. A subscript following a symbol and a number in front of a symbol do not represent the same thing. Please note it. Okay. And compounds are formed when two or more elements chemically combine, resulting in the formation of bond. And empirical formula is actually another simplified representation of molecular formula. And if we know a compounds formula, then we can just easily define the empirical formula. Okay, compounds with the same molecular formula may have different atom-to-atom bonding and therefore different structures. Actually, there exist many types of isomers. Some of them are structural and some of them are spatial. A modern periodic table arranges elements in increasing order of their atomic numbers and group atoms with similar properties in the same vertical column. The elements are arranged in 7 horizontal rows called periods or series and 18 vertical columns called groups. We can sort the elements into large classes with common properties: metals for elements that are shiny, malleable, good conductor; non-metals for elements that appear dull, poor conductor; and metalloids for those that can conduct heat and electricity moderately well and possess some properties of metals and some properties of non-metals. Elements in groups often behave in a somewhat similar manner. This is partly due to the number of electrons in the outer shell and their similar radius as the bond. Okay, that's good. That's a quick recap for you. And now let's move to today's discussion. Okay, we are ready to cover more about ionic and molecular covalent compound. I mean, not actually. First, we need to know about the bond, and second, we'll discuss about the compound. Okay. So, in ordinary chemical reactions, the nucleus of each atom and thus the identity of the atom remains unchanged. Electrons, however, can be added to atoms by transfer from other atoms or lost by transfer to other atoms or shared with another atom. The transfer and sharing of electrons among atoms govern the chemistry of the elements. During the formation of some compounds, atoms gain or lose electrons and form electrically charged particles called ion. Please see the figure below. This is the natrium, the sodium atom, and the sodium ion. Okay, so you see that the sodium plus ion. Okay, it means that it is positively charged by one charge. It means that it has lost one electron, and it means that now it the atom consists of more protons than electrons. Then it will be positively charged. We can use the periodic table to predict whether an atom will form an anion or a cation, and we can often predict the charge of the resulting ion. Atoms of many main group metals lose enough electrons to leave them with the same number of electrons as an atom of the preceding noble gas. To illustrate, an atom of an alkali metal, group 1, loses one electron and forms a cation with a positive 1 charge. An alkaline earth metal, group 2, loses 2 electrons and forms a cation with a positive 2 charge, and so on. For example, a newer calcium atom with 20 protons and 20 electrons readily loses 2 electrons. This results in a cation with 20 protons, 80 electrons, and a positive 2 charge. It has the same number as electrons as atom of the preceding noble gas, argon, and it is symbolized as Ca2+. The name of a metal ion is the same as the name of the metal atom from which it formed, so Ca2+ is called a calcium ion. Okay, so you actually don't need to say how much charge it lost or gain because it is quite obvious. Okay, calcium ion. When atoms of non-metal elements form any ions, then generally it gains enough electrons to give them the same number of electrons as an atom of the next noble gas in the periodic table. Say, for example, atoms of group 17 will gain one electron and form anions with with a negative one, a minus one charge. Atoms of group 16 gain two electrons and form ions with negative 2 charge, and so on. For example, the near bromine atom with 35 protons and 35 electrons can gain 1 electron to provide it with 36 electrons. This results in an anion with 35 protons, 36 electrons, and a negative charge. It was the same number of electrons as atoms of the next noble gas, krypton, and it is symbolized as Br minus. Note that the usefulness of the periodic table in predicting likely ion formation and charge. Moving from the far left to the right of the periodic table, main group elements tend to form cations with a charge equal to the group number. That is, group 1 elements form positive 1 ions, group 2 elements form positive 2 ions, and so on. By moving from the far right to the left on the periodic table, elements often form anions with a negative charge equal to the number of groups moved left from the noble gases. For example, group 17 elements, one group left of the noble gases, will form negative 1 ions. Group 16 elements, two groups left, will form negative 2 ions, and so on, so on. This trend can be used as a guide in many cases, but be careful, its predictive value decreases when moving toward the center of the periodic table. In fact, transitional metals and some other metals often exhibit variable charges and that are not predictable by their location in the table. For example, copper can form ions with a positive 1 or positive 2 charge, and iron can form ions with a positive 2 or positive 3 charge. So be careful. The ions that we have discussed so far are called monoatomic ions or monatomic ions. That is, they are ions formed from only one atom. We also find many polyatomic ions, and these ions, which act as discrete units, are electrically charged molecules or a group of bonded atoms with an overall charge. Some of the more important polyatomic ions are listed in the table below. Please pay attention, take a screenshot if it is needed. Oxygen, Oxyanions are polyatomic ions that contain one or more oxygen atoms. It is very clear from the name oxygen, and anion. So oxyanions are polyatomic ions that contain one or more oxygen atoms. Note that there is a system for naming some polyatomic ions. 8 and ite are suffixes designating polyatomic ions containing more or fewer oxygen atoms. Per, short for hyper, and hypo, meaning under, are prefixes meaning more oxygen atoms than 8 and fewer oxygen atoms than 8, respectively. For example, perchlorate is ClO4 minus, chlorate is ClO3 minus, chloride is ClO2 minus, and hypochlorite is ClO minus. Unfortunately, the number of oxygen atoms corresponding to a given suffix or prefix is not consistent. For example, nitrate is NO3 minus, while sulfate is SO4 2 minus. This will be covered in more detail in the next module on nomenclature. The nature of the attractive forces that hold atoms or ions together within a compound is the basis for classifying chemical bonding. When electrons are transferred and ions form, ionic bonds result. Ionic bonds are electrostatic forces of attraction, that is, the attractive forces experienced between objects of opposite electrical charge, in this case cations and anions. When electrons are shared in molecular form, then covalent bond results, or molecular bond results. Covalent bonds are the attractive forces between the positively charged nuclei of the bonded atoms and one or more pairs of electrons that are located between the atoms. So compounds are classified as ionic or molecular or covalent on the basis of the bonds present in them. Now let's start discussing from ionic compounds. When an element composed of atoms that readily lose electrons, metal reacts with an element composed of atoms that readily gain electrons, a non-metal. A transfer of electrons usually occurs, producing ions. The compound formed by this transfer is stabilized by the electrostatic attraction or the ionic bonds between the ions of opposite charge present in the compound. For example, each sodium atom in sample of sodium metal, group 1, gives us 1 electron to form a sodium cation, Na+, and each chlorine atom in a sample of chlorine gas, group 17, accepts 1 electron to form a chloride anion, Cl-. The resulting compound, NaCl, is composed of sodium ions and chloride ions in a ratio of 1 Na+ ion for each Cl- ion. Similarly, each calcium atom, group 2, can give 2 electrons and transfer 1 to each of the 2 chlorine atoms to form CaCl2, which is composed of Ca2+ and Cl- ions in a ratio of 1 Ca2+ ion to the 2 Cl- ions. A compound that contains ions and is held together by ionic bonds is called ionic compound. The periodic table can help us recognize many of the compounds that are ionic. When a metal is combined with one or more nonmetals, then the compound is usually ionic. However, it is not always true. For example, for aluminum chloride, AlCl3, it is not ionic. So there are some exceptions. You can often recognize ionic compounds because of their properties. Ionic compounds are solids that typically melt at high temperatures and boil at even higher temperatures. For example, sodium chloride melts at about 801 degrees Celsius and boils about 13 degrees Celsius. In solid form, an ionic compound, an ionic compound is not electrically conductive because its ions are unable to flow. When molten, however, it can conduct electricity because its ions are able to move freely through the liquid. See the demonstration on the next slide. Yeah, this is the demonstration. So you see, when it is melted, then the electricity can flow and the bulbs light up. So in every ionic compound, the total number of positive charges of the cations equal to the number of negative charges of the anions. Thus, ionic compounds are electrically neutral overall, even though they contain positive and negative ions. We can use this observation to help us write the formula of an ionic compound. The formula of an ionic compound must have a ratio of ions such as the number of positive and negative charges are equal. Many ionic compounds contain polyatomic ions as the cation, the anion, or both. As with simple ionic compounds, this compound must also be electrically neutral, so the formula can be predicted by treating the polyatomic ions as a discrete unit. Okay, we use the parentheses. For example, you see the formula of calcium phosphate is Ca3 in bracket PO4 2. This formula indicates that there are 3 calcium ions, Ca2+, for every 2 phosphate groups, PO4 3 minus. So the PO for 3 minus groups are discrete units. It's consisting of 1 phosphorus atom and 4 oxygen atoms and having overall charge of 3 minus. Because an ionic compound is not made up of single discrete molecules, it may not be properly symbolized using a molecular formula. Instead, ionic compounds must be symbolized by a formula indicating the relative numbers of its constituent ions. For compounds containing only monatomic ions, such as NaCl, and for many compounds containing polyatomic ions, such as CSO4. However, the formula for some ionic compounds containing polyatomic ions are not empirical formulas. For example, the ionic compound of sodium oxalate is comprised of Na plus and C2O4 2 minus ions combined in a 2:1 ratio, and its formula is written as Na2C2O4. Oh, how tiring. The subscripts in this formula are not the smallest possible whole numbers, as each can be divided by 2 to yield the empirical formula NaCO2. But this is not exact formula for sodium oxalate, however, as it does not accurately represent the compound's polyatomic anion C2O4 2 minus. Okay, we are done with the first type of compound. Now let's explain about molecular compound. Many compounds doesn't contain ions but instead consist solely of discrete neutral molecules. And these molecular compounds, covalent compounds, result when atoms share rather than transfer or gain lose electrons. We are often identify molecular compounds on the basis of their physical properties. Under normal conditions, molecular compounds often exist as gases, low boiling liquids, and low melting solids, although many important exceptions exist. Whereas ionic compounds usually form when a metal and a non-metal combine, covalent compounds usually form when a combination of non-metals. Thus, the periodic table can help us recognize many of the compounds that are covalent. While we can use the position of a compound's element in the periodic table to predict whether it's ionic or covalent at this point in our study of chemistry, you should be aware that this is a very simplistic approach that doesn't account for a number of interesting exceptions. Okay, so we are done for this lesson, and let's practice to see how you understand this concept well. First problem: a meteorite found in central Indiana contains traces of the noble gas neon picked up from the solar wind during the meteorite's trip through the solar system. Analysis of a sample of the gas showed that it consisted of blah 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 neon 20 and blah 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 neon 21 and blah 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 neon 22. What is the average mass of the neon in the solar wind? It is clear you just need to input the formula. You just need to plug in the value, substitute in the formula given on the, I think, the fifth or the sixth slide. Okay, so we are done. That's the answer for you. I want you to review by yourself. Okay, nothing to be explained here. Very clear. Second problem: naturally occurring chlorine consists of chlorine 35 and chlorine 37, with an average mass of this 35.453 AMU. What is the percent composition of chlorine in terms of these two isotopes? Okay, so the average mass of chlorine is just a fraction, that is chlorine 35 times the mass of chlorine 35 plus a fraction that is chlorine 37 times the mass of chlorine 37. And you just need to make a fraction. For example, you represent the fraction compound of Cl35 as x. Then the fraction that consists of Cl37, it is 1 minus x. By doing this, you can just substituting this to the average mass equation, and you obtain that chlorine consists of 75 point. Actually, that is point, not comma. I'm sorry. Okay, actually in my country I use comma, not point. Okay, so 75.76% chlorine 35 and 24.24% chlorine 37. I mistyped it again, not 34, 37. I'm sorry. Third problem: molecules of glucose, blood sugar, contain 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. What are the molecular and empirical formula of glucose? It's very easy, right? So the molecular formula, it is very clear: C6H12O6. Done. And the empirical formula, the simplest whole number ratio, 1 by 2 by 1. So CH2O. Done. Okay, very easy. Number 4. Atoms of each of the following elements are essential for life. Give the group number for following elements: chlorine, calcium, sodium, and sulfur. Now check your periodic table that you have printed, and you can now easily determine which family name of each element belongs to. And the answer is chlorine belongs to halogen, calcium belongs to alkaline earth metal, sodium belongs to alkali metal, and sulfur belongs to chalcogen. Done. Number 5. An ion found in some compounds used as antiperspirants contains 30 protons and 10 electrons. So why is this symbol? Okay. So because the number of protons remains unchanged when an atom forms an ion, so the atomic number of the element must be 30. Very clear. But we know that from the periodic table that the element with 13 proton or the number of atom 13, that is aluminum or aluminium. It depends on you how to read it. Okay, so the aluminum atom has lost 3 electrons and thus has 3 more positive charges than it has with its electrons. So it is just an aluminum cation, which is Al3 plus. Done. Number 6. Magnesium and nitrogen react to form an ionic compound. Please predict which forms an anion, which forms a cation, and the charges of each ion. Write the symbol for each ion and name them. So here's the solution. Magnesium position in the periodic table is group 2, which tells us that it is a metal, and metals will form cation. A magnesium atom must lose 2 electrons to have the same number of electrons as the atom of the previous number gas, neon. Thus, a magnesium atom will form a cation with 2 fewer electrons than a proton and a charge of positive 2. Whereas the symbol the symbol of the ion is Mg2 plus, and this is called magnesium ion. Whereas the nitrogen is positioned on group 15, and it represents that it is non-metal. Non-metal will form negative ions, which is anions. A nitrogen atom must gain 3 electrons to have the same number of electrons as of the atom of the following noble gas, 9. Thus, a nitrogen atom will form an anion with 3 more electrons than protons and a charge of negative 3. The symbol for this is N3 minus, and it's called nitride ion. Okay, done, done, done. Okay, number 7. The gemstone sapphire is mostly a compound of aluminum and oxygen that contains aluminum cations Al3 plus and oxygen anions O2 minus. What is the formula of the compound? Okay, so because we know that ionic compound must be electrically neutral, then it must have the same number of positive and negative charge. 2 aluminum ions, each with a charge of 3 plus, could give us 6 positive charge, and 3 oxide ions, each with a charge of 2 minus or negative 2. I always say negative 2, I write it as 2 minus, will give us 6 negative charges. So the formula will be Al2O3. Number 8. Baking powder contains calcium dihydrogen phosphate, an ionic compound composed of ion Ca2 plus. I'm sorry, the 2 plus must be superscript. I don't know, I always mistype it. Okay, and H2PO4 minus. What is the formula of this compound? Here's the solution for you. So the positive and negative charge must be balanced, and this ionic compound must be electrically neutral. Thus, we must have 2 negative charges to balance the 2 positive charge of the calcium ion. And this requires a ratio of 1 Ca2 plus, also supposed to be superscript, to 2 H2PO4 minus ions. We designate this by enclosing the formula for the dihydrogen phosphate ion in parentheses and adding a subscript 2. Then the formula is Ca and in parentheses H2PO4 2. Done. Number 9, the last question, the last problem. Okay, predict whether the following compounds are ionic or molecular. Ki H2O2 CaCl3 Li2CO3. I hope you can name this. Okay, or maybe not in this lesson. Okay, the next lesson. Okay, the first one. Potassium, group 1, is a metal, and iodine, group 17, is a non-metal. So Ki is predicted to be ionic. The second one is hydrogen, group 1, is a non-metal. While oxygen, group 16, it is a non-metal too. So it is predicted to be molecular, right? And point C, carbon. Group 14 is a non-metal. Hydrogen, group 1 is a non-metal. And chlorine, group 7 is also a non-metal. So CHCl3 is predicted to be molecular. D. Lithium, group 1 is a metal. And carbonate is a planetary ion. So Li2CO3 is predicted to be iodic. Done. So we are now moving to assignment. Here's the assignment for you today. I want you to take screenshot and do it by yourself. I provided the answer, but please don't cheat it. Because of I give you the answer, it doesn't mean that you have solved it. You need to try to find the answer, okay? So the answer is just to check if your answer is correct or not. Okay. This is the second slide. Please take a capture. Okay, we are done with our lesson today, and here another quote for you for today. Okay. So Mandy Hale once said, growth is painful, change is painful, but nothing is as painful as staying stuck somewhere you don't belong. Okay? Because the only thing in this world actually this is always true is change. Yeah, we need to always adjust, adapt to the change. This is painful. This is not what we want, but be stuck in comfort zone and don't do something. We don't gain something. It is much worse than what you may think. Okay. Okay. So that's all for the lesson today. Thanks for watching. Please subscribe, give a like, comment, and share this video to your friends. And my class will be on Tuesday and Thursday every week. As usual, keep watching and be thoughtful. Goodbye. See you. Cheers.